Hi everyone, welcome to Lecture 3 Part 1 on simple and complex properties. The objectives for this video are the following. After watching, everybody should be able to: Number 1, describe the structure of simple and complex properties. Number 2, construct presence tables for complex properties. And number 3, define the terms logically equivalent, mutually exclusive, universal property, null property, and contingent property for complex statements. Now, over the last two lectures, we've looked at simple and complex statements and truth tables for statements. This lecture presents analogous concepts for properties as opposed to statements. The good news is that the skills we've built over the last few lectures transfer over to the analogous concepts that involve properties, so there isn't anything new in this lecture in terms of skill development. Recall from Lecture 2 Part 1 then that a characterizing expression characterizes the thing that's being referred to in a statement. Another way of saying this is that the characterizing expression ascribes a property to the thing that's being referred to. Properties then are just the predicates we met when we talked about characterizing expressions. So if we think back to this example, the coffee cup is blue. We said before that the characterizing expression here is blue. Another way of saying that is that the characterizing expression ascribes the property, or the one-place predicate, blue, to the thing it refers to the coffee cup. So let's pause for a quick question. Now, just as we can build complex statements out of simpler ones using the logical connectives we've seen, and, or, and not, we can build complex properties out of simpler ones using the same logical connectives. For example, here's a bunch of properties: blue, plastic, and metal. Combining them using the logical connectives, we can form, for example, the complex property blue and not plastic or metal. This is the sort of thing you do when you make Boolean searches on databases like Google. It tells the database to search entries that are blue and neither plastic nor metal. In this course, we'll use capital letters to abbreviate property expressions, and the book does that too. So a natural way to abbreviate the above example would be something like B wedge not PVM, where obviously B stands for blue, P for plastic, and M for metal. Here's a quick question on complex properties, so let's pause for a second. Now, to analyze the truth of complex properties, we use an analogous method to the one we use to analyze the truth of complex statements. The method we used there was truth tables, and we call the method used to analyze the truth of complex properties presence tables. This is just because we describe properties as being present or absent rather than true or false, which we did in the case of statements. The presence or absence of a complex property then depends on the presence or absence of that property's simple constituents in exactly the same way that the truth of a complex statement depended on the truth of its simple constituent statements. And in particular, the rules for not, and or in presence tables are exactly analogous to the rules we saw for truth tables. So we have the negation of a property is present, just in case the property is absent. So the table for negation looks like this. Here F abbreviates a property, A stands for absent, and P stands for present. So comparing this presence table to the truth table for not, we can see that present is analogous to true, and absent is analogous to false. So let's look at and next. Here the rule is, we say a conjunction of properties is present just in case both of the properties are present. And so the table for and is this, the presence table. And we can see that this table is analogous to the truth table for and in the same way, where the simpler constituent properties are F and G, and we have present in place of true and absent in place of false. Finally, we say that a disjunction of properties is present just in case at least one of the properties is present. So the presence table for or is this one, which again is analogous to the truth table for or, with present in place of true and absent in place of false. We calculate the presence table for complex properties that we've built out of simpler ones using the logical connectives in exactly the same way that we calculated the truth tables for complex statements. So to get a better handle on that, here's an example. This is the one from the book. It's on page 8. So here's a complex property, not f v g. It's built out of two simpler properties, f and g, using not and the v symbol, or. Now we want to calculate the presence table for the complex thing, not f v g. So we begin by recording f and recording g and the different property combinations that they might take. Now instead of just modeling this example, there'll be a few questions throughout it, so here we go. So in row 1 we have present present, so both f and g are present. In row 2 we have f present and g absent. In row 3 we have f absent and g present. And in row 4 we have both f and g absent. Now this is exactly analogous to how we recorded the truth and falsity combinations for two statements p and q like we did last time. So the next thing we do, we look at the next largest complex property out of the whole complex property that we're interested in, such that we can calculate its presence table in one step from the values that we have in the table, from the values of f and g. When we do that, we see that the next largest property is not f. We need to know the value of not f before we can calculate the value of this whole disjunction, not f v g. So we're going to do not f first. So next we record not f in the table, and we can calculate its presence table using the presence table for f that we already have in the table. So here's one question. What is the presence table for not f here? So we should have this. In the first two rows, f is present, so by the negation rule, we know that not f is absent in those two rows. And in the third and fourth rows, f is absent, so by the rule for negation, we know that not f is present in those rows. So that is the presence table for not f. And finally, we see that the next largest complex property, such that we can calculate its presence table in one more step from what we already have in our table, is the whole property of interest, not f v g. So we have the presence table for not f, and we have the presence table for g, so we just need to apply the presence rule for disjunction to calculate the presence table for the whole complex statement. So have a go yourselves before I go through it. Which of these presence tables is correct for not f v g? Okay, so in row 1 we've got not f absent and g present. Now by the disjunction rule we know a disjunction of properties is present just in case at least one of the properties is present. In this case g is present, so at least one is present. So by the rule, the disjunction of properties not f v g is present. In row 2, we've got not f absent and g absent. So in this case, neither disjunct is present. So by the rule, not f v g is absent. In row 3, we've got not f present and g present. So in this case, both disjuncts are present, so at least one is present. So by the rule, the disjunction not f v g is present. And finally, in row 4, we've got not f present and g absent. So at least one disjunct is present, this time it's not f. So by the rule, the disjunction not f v g is present. So that's the presence table for the complex property not f v g, and in general that's how the presence tables for complex properties are calculated. It's exactly analogous to the method for truth tables. Again, practice makes perfect with this stuff, so have a good go at the large group problems and the assignment questions to get good at this stuff. Now, to finish off, we'll make some analogous definitions to those we made last time in the case of statements and truth tables. So we say the following things in the case of properties. Two complex properties are logically equivalent if they are present in exactly the same cases. So here by cases, I'm thinking of rows in presence tables. So to check whether two complex properties are logically equivalent, you construct the presence tables for each of them, and then you compare the columns for the two properties being compared. You see whether they agree in every row of their truth tables. And we say that two complex properties are mutually exclusive if there's no case in which they are both present. So to check whether two complex properties are mutually exclusive, you construct the presence tables for each of them, and you look at the columns for the two properties being compared, and you see whether there are any cases in which they're both true. And if there are not, then they are mutually exclusive. Now, notice that the terms logically equivalent and mutually exclusive are the same terms we used before when we were talking about statements. It's just that really there are two separate definitions. There is one for statements and there's another for complex properties. So next, analogously to last lecture, we call a property that's present in all cases a universal property. This is analogous to tautologies from before. On the other end of the spectrum, we call a property that's absent in all cases a null property, and this is analogous to contradictions from before. And finally, we call a property that's neither universal nor null a contingent property, and this is the same terminology that we had for statements. So to check whether a complex property is universal, null, or contingent, you would construct its presence table, and you would look at the values in the final column and see which ones fit which definition. So here's one last question before we wrap up. Okay, so that's where we'll finish for today. We'll polish off chapter 1 in the next video, which is about validity. So just before we finish, do your self-reflections, and I'll see you all next time.